The year was 1891. Imagine walking into a factory, the air thick with steam, the floor vibrating under your feet. Around you, hundreds of machines hum in unison. Everything seems routine, calm even. But inside the engine room, a sleeping giant waits. A 56-ton flywheel spinning silently, holding energy that could rival a small battleship. And on this day, that calm would erupt into chaos. Suddenly, the wheel shattered. Iron fragments tore through brick walls like bullets. Timber beams snapped, and the deafening roar of destruction echoed through the mill. 3 men died instantly, their lives erased in the blink of an eye. Steam hissed violently from ruptured pipes, dust filled the air, and panic rippled across the floor. Workers who had passed this spinning giant every day, feeling only a subtle hum under their feet, were now confronted with its lethal force. What was supposed to keep the factory running smoothly had turned into a weapon of unimaginable destruction. How could a machine designed to stabilize and power a factory become such a deadly threat? What kind of energy could a single flywheel store, and why didn't anyone see the danger coming? The story of these hidden giants is not just a tale of mechanical failure. It's a story about human ambition, miscalculated risk, and invisible forces that could obliterate life without warning. Factories of the 19th century were obsessed with efficiency. Steam engines surged in pulses, threatening to snap threads, jam looms, and destroy products. Enter the flywheel, a massive cast-iron wheel designed to absorb the violent swings of steam power, spinning day and night to deliver smooth motion. To the human eye, it moved almost gracefully, but its rim, weighing tons, traveled faster than a sprinting horse. Every pound of iron at the edge carried a secret force, an energy that was predictable in math, but invisible to humans. Workers accepted the hum as background noise, the ever-present giant as a silent partner in production. But the hidden danger was real, and it was waiting for the tiniest flaw, a hairline crack, a failed bolt, or a minor mechanical misalignment. Once that tension broke, the energy stored for hours erupted in an instant. Walls became sieves, floors became launch pads, and ordinary industrial work turned into life-or-death survival. This is the story of the spinning giants that powered factories and terrified workers. Machines so massive, so silent, and so trusted that they became invisible hazards in plain sight. What happened inside those mills holds lessons far beyond history, lessons about risk, power, and the unseen forces that shape our world. And in the next few minutes, you'll see why industrial ambition turned these spinning giants into silent predators waiting for the perfect moment to strike. So, if you think you've seen dangerous machines before, think again. By the end of this story, you'll never look at a factory or a spinning wheel the same way again. The question is, if you were standing just feet away from one of these hidden giants, could you survive its fury?
Now that you've glimpsed the terrifying force of these spinning giants, it's time to meet the star of the story, the industrial flywheel. But don't let its seemingly simple shape fool you. A giant cast-iron disc spinning in the shadows of a mill isn't just a machine. It's the beating heart of the factory, the unseen engine behind every loom, press, and pump. And it's more powerful than anything most people could imagine. Picture this. A wheel so enormous it could fill an entire room, its rim just feet from the workers' walkways. Some measured over 30 feet in diameter, weighing more than 100 tons. That's heavier than a fully loaded city bus. And yet, it rotated slowly, almost gracefully, at around 50 to 60 revolutions per minute, a deceptive calm hiding its true power. Each rotation stored energy so intense that if released suddenly, it could tear through brick walls, splinter timber, and send shards of iron flying like missiles. These flywheels weren't just machines, they were problem solvers. In the 19th century, steam engines delivered power in pulses. Every piston stroke surged, then fell. For a textile mill, this was catastrophic. Threads snapped, looms jammed, and production faltered. Enter the flywheel. It absorbed the jerky, uneven energy and released it smoothly, allowing hundreds of machines to operate in harmony. It was efficiency turned into iron. But here's the chilling part. Flywheels were not optional backups. They were essential, the linchpin of the entire operation. One wheel could power hundreds of machines simultaneously, linking looms, carding machines, presses, and pumps to a single engine. If the flywheel slowed, the entire factory slowed. Stopping it from maintenance was expensive and risky. Restarting a steam engine required hours, fuel, and labor. That's why these wheels ran continuously for weeks, almost like a sleeping predator coiled inside the mill. The materials used were deceptively simple. Cast iron, poured in massive molds, and bolted together. Steel existed, but it was expensive and harder to produce in such large sections. The engineers relied on thickness, weight, and inertia to hold the machine together, trusting calculations and history rather than fail-safes. But in the heart of the engine room, there was no blast wall, no warning system, no cushion, just a spinning mass of iron carrying enough energy to rival industrial boilers. Here's a question that'll make your stomach tighten. If a flywheel is spinning silently, calmly, and has been trusted for decades, how can you possibly predict when or if it might fail? How can hundreds of tons of energy stored invisibly in a disk of iron suddenly erupt and destroy everything in its path? This is why engineers called it the heart of the mill. Its motion powered entire cities indirectly, kept profits flowing, and made the impossible seem routine. And yet, its quiet presence masked a terrifying truth. The bigger the wheel, the greater the stored force, and the smaller the margin for error. Every bolt, every casting joint, every tiny imperfection in the iron mattered, because one miscalculation, one microscopic crack could turn this trusted servant into a deadly weapon. By understanding the flywheel, you'll start to see why these industrial machines were more than metal. They were forces of nature in disguise, combining science, ambition, and risk. And as we move to the next chapter, you'll discover the hidden dangers engineers never fully realized, dangers that would test human courage, ingenuity, and luck in ways few could imagine.
If the flywheel seems impressive, efficient, and almost elegant, that's only half the story. Behind its spinning calm lurks a danger few could see and even fewer understood. Imagine a machine weighing over 100 tons, rotating silently inside a brick-and-mortar mill, carrying more energy than a dozen industrial boilers combined. Its power was invisible, yet every second it spun, it was a ticking time bomb. Engineers designed these wheels to solve problems, not create new ones. But the bigger the flywheel, the more energy it stored and the higher the stakes. Centrifugal force pulled at every pound of iron at the rim, stretching it with relentless tension. Cast iron, strong under compression but weak under tension, carried this stress silently. Microscopic cracks formed inside, unseen, growing day by day as the wheel heated, cooled, and endured constant load cycles. To the human eye, the wheel looked perfectly fine, but internally it was a pressure cooker of potential destruction. Here's the frightening truth. The failure of a flywheel wasn't gradual. It didn't warn you. There were no alarms, no flames, no whistle to signal danger. One moment the wheel was rotating steadily, the next a crack could split the rim, unleashing hundreds of tons of kinetic energy in a fraction of a second. Pieces of iron would shoot outward like bullets, punching through brick walls, timber beams, and anything or anyone in their path. The energy stored was unstoppable, and once released, there was no turning back. Now consider the challenge the engineers faced. How do you control a machine of this size and energy inside a crowded factory? The answer, surprisingly, was trust and calculation. They relied on mechanical governors, simple balance-based devices that regulated speed.
But a small failure, a 10% overspeed, a worn bolt, a hidden crack could increase internal stress exponentially, pushing the iron past its breaking point. No matter how careful, human error, material fatigue, and sheer scale conspired against them. Even routine operation carried risk. Workers passed these spinning giants daily, feeling vibrations but unaware of the invisible tension in the rim. Every bolt, every casting joint, every slight imperfection mattered. A flywheel failure didn't just damage machines, it threatened human life and entire factories. And yet, stopping the wheel for inspection was often impossible. Downtime was costly, and engineers trusted history more than theory. The question hanging over every mill was terrifying. How much energy is too much? How can you predict the unpredictable? Each spinning giant was a puzzle of forces, a challenge of physics, and a gamble with fate. And while the engineers built for efficiency, they never fully designed for failure. That unspoken risk became the hidden challenge of industrial progress, controlling power that could destroy from the inside out. In this chapter, the audience begins to realize that the flywheel wasn't just a machine, it was a coiled storm, a silent predator lurking in plain sight. Its spinning motion stored energy invisibly, yet it threatened to erupt at any moment. And it's here that we start to see the human side of the story, the men who worked alongside these mechanical monsters, unaware of just how close they were to disaster. Next, we'll dive into the lives of those workers, their daily exposure to hidden danger, and the choices they made while working in the shadow of these industrial titans. Because understanding human perspective will make the eventual disaster all the more shocking.
To understand the real stakes, we need to step off the blueprint and into the boots of the men who worked beside these spinning giants every day. Imagine walking into a giant mill, the air thick with steam, the smell of oil and hot iron, the constant hum of machinery vibrating through the floors, walls, and even your chest. And there, dominating the room, sat a flywheel the size of a small house, spinning silently, yet carrying enough force to obliterate everything around it if it failed. For workers, this wasn't just a machine, it was a constant presence, a mechanical heartbeat dictating the rhythm of their lives. Every step, every turn of a wrench, every adjustment to the looms depended on that wheel turning smoothly. Stop the wheel and productivity collapsed. Push it too hard and disaster could strike. They were coexisting with a force they couldn't see but could feel. Vibrations in the floor hinted at the immense energy beneath their feet, a subtle reminder that they were working next to a potential tornado of iron. Yet the men carried on, often blind to the true danger. Their perspective was shaped by routine and familiarity. Years of steady operation bred confidence, even complacency. "It's just a wheel," they would joke, unaware that each cast iron spoke, each bolted joint was silently holding back hundreds of tons of kinetic energy. Their lives depended on trust in the engineers, the materials, and, most dangerously, the wheel itself. Breaks were rare, and downtime almost unthinkable. The workers understood one fact intimately: the factory never sleeps. The flywheel turned night and day, powering hundreds of machines simultaneously, looms, carding machines, pumps, all synchronized by the rotation of this massive iron disc. A single hesitation in motion could snap threads, jam machinery, or ruin entire batches of product, making human skill and precision essential. But danger wasn't theoretical, it was immediate. Every day, men walked within feet of the spinning rim, sometimes even under it, adjusting belts or greasing bearings. They worked amidst an invisible trap. Centrifugal force pulled relentlessly at the iron, tiny cracks formed, and fatigue silently grew. Nobody saw it, nobody heard it, and that was the terrifying beauty of the threat.
It lurked in plain sight, normalized by repetition, hiding its catastrophic potential behind a mask of calm. Curiosity and fear intertwined. Workers asked themselves questions quietly. What if this rim snaps? What if a bolt fails? How far could it reach? Could 100 tons of iron really kill? They were aware of the risks. Some had heard of explosions in neighboring mills, but they didn't truly know until tragedy struck. That tension between awareness and helplessness defined every shift. Here lies the core human drama. The flywheel wasn't evil, but it demanded respect. The men's lives depended on understanding the machine, but the machine's true power was almost unknowable until it was too late. And this daily coexistence created a unique perspective. 1 foot in normal life, 1 foot teetering on the edge of disaster. By stepping into their shoes, we feel the stakes of industrial progress, not just in steel and iron, but in human lives. And it's this perspective that makes the eventual disaster heart-pounding and gut-wrenching, because we've walked alongside the workers, felt their trust, their routine, and their fragility. Next, we'll travel back in time to uncover the historical origins of these massive flywheels, showing why engineers thought this invisible danger was worth the risk, and how human ambition and industrial necessity collided with physics in the most spectacularly dangerous ways.
To truly understand why these flywheels became hidden giants of destruction, we have to travel back to the late 19th century, a time when steam ruled industry and factories were the beating hearts of towns. Picture a Manchester or Pittsburgh in the 1880s, chimneys puffing smoke into the sky, streets crowded with workers, and inside massive brick mills, machines clattering in precise chaos. Power wasn't delivered through electricity. It came from steam engines pulsing like giant mechanical hearts, surging with energy in uneven, unpredictable bursts. Engineers faced a challenge that seems almost impossible today. How do you take unreliable, jerky motion from a piston and turn it into smooth, continuous power for hundreds of machines at once? The answer was deceptively simple. Massive flywheels, heavy discs of cast iron, sometimes reaching 30 to 40 feet in diameter and weighing over 100 tons. These wheels were not ornamental, they were the core of the system, absorbing surges, storing energy, and keeping factories running without interruption. But here's the paradox. The bigger they got, the more efficient they were, and the deadlier they became. Flywheels were symbols of industrial ambition. They allowed factories to expand production, streamline operations, and increase profits. Every new textile mill or steelworks aimed to outsize the last, with larger wheels spinning faster and heavier than ever before. Engineers and factory owners calculated efficiency but underestimated danger. Their math accounted for load, speed, and inertia, but not the invisible cracks forming deep inside the cast iron rim. Stress and fatigue accumulated silently, while workers and managers trusted history, routine, and brute strength to keep them safe. The historical record is chilling. Engineering journals from the 1990s are full of reports detailing flywheel bursts across North America and Europe. From textile mills in Manchester, New Hampshire, to steel plants in Pennsylvania, a recurring pattern emerges. High-speed iron turning indoors, operating close to its material limits, surrounded by people. These weren't freak accidents, they were predictable consequences of scaling machines beyond common sense. Yet industrial culture rewarded ambition over caution. Failure was measured by output lost, not by risk ignored. And the societal drive to produce never paused for safety. Even more striking is how normalized this danger had become. Engineers believed flywheels could last decades if properly maintained.
Failure was treated as an anomaly, often blamed on a single defect, a faulty bolt or improper lubrication, never on the fundamental design. But behind the calculations and confident reports lurked a dark truth. Every additional foot of diameter, every extra ton of mass exponentially increased stored energy. What worked for 20-ton wheels became a time bomb at 100 or 200 tons. And the public, they were blissfully unaware. Entire communities lived and worked within sight of spinning iron giants, with no sense of the latent catastrophe around them. Factories were packed tightly, engine houses at the center, streets and homes surrounding them. Any failure had the potential to extend far beyond the mill walls. The lesson of this historical chapter is clear. Ambition without foresight breeds disaster. The story of Flywheels isn't just about machines, it's about an era when industrial progress collided with human limits. Understanding this backdrop gives us a chilling perspective. What seems like innovation can easily become a weapon, and the cost of ignoring subtle danger is measured in lives, not profits. Next, we'll move to Chapter 6, the disaster moment, where all these tensions, engineering, human perspective, and hidden energy explode in the most dramatic and catastrophic way imaginable.
The stage was set. The flywheel, massive, silent, deceptively calm, spun like a mechanical giant in the heart of the Amoscave Manufacturing Company mill. To the casual observer, it was just another machine. But inside, it was a ticking time bomb of concentrated energy, storing force equivalent to multiple industrial boilers, waiting for a single flaw to release its deadly fury. On a seemingly ordinary day in 1891, everything changed in less than a heartbeat. 3 men were in the engine room, performing routine tasks, unaware that the very wheel keeping their factory alive was on the brink of catastrophe. Then it happened. A shattering crack erupted across the cast-iron rim, invisible to the human eye until it was too late. The energy that had been safely spinning for hours had nowhere to go, and the flywheel exploded with brutal precision. Iron fragments tore through the air at speeds faster than a sprinting horse. Brick walls, built to hold weight, offered no resistance. Timbers splintered, cast iron columns shattered like glass. The deafening sound of destruction filled the mill, followed by a silence so sudden it felt unnatural. The 3 men near the wheel were gone in an instant, casualties of a machine that betrayed the very workers it had sustained. But the devastation didn't stop there. Pieces of iron, some weighing hundreds of pounds, traveled across the engine room, punching through walls and machinery, turning everyday objects into deadly projectiles. Windows shattered, glass rained down like knives, roof beams splintered, casing sections of the factory. Each fragment carried the force of stored energy, a silent assassin with no warning, proving that size and mass magnify danger in ways the human mind struggles to comprehend. Outside the engine room, panic spread. Workers in neighboring rooms had no chance to react. The shock wave of destruction reached beyond the mill walls. Iron fragments landed hundreds of feet away, some crossing the Merrimack River, damaging other buildings and forcing entire factory complexes to halt operations immediately. Families gathered at mill gates, staring in disbelief at the carnage. Rumors outpaced facts, spreading fear through the town faster than anyone could comprehend. What made this disaster terrifying was not just its scale, but its speed and invisibility. The wheel's failure lasted less than a second. No time to shout, no time to escape, only the sudden realization that the source of power had become a force of destruction. Engineers and investigators arrived afterward to measure damage, recover fragments, and tally casualties, but the human experience, the fear, the chaos, the shock, was impossible to quantify.
The Amos-Gay event was a lesson carved in iron and brick. When energy is concentrated without control, disaster is inevitable. Every spin, every ton of cast iron, every unnoticed crack built toward this moment. The disaster moment teaches us more than numbers or reports. It reveals the fragile line between human ingenuity and hubris, the danger of invisible forces harnessed carelessly, and the tragic cost when the boundary between machine and human is ignored.
The aftermath of the Amos-Gay flywheel disaster didn't just leave a few broken walls and mangled machinery. It shattered the very sense of security for workers, factory owners, and the surrounding community. What had been invisible power, humming silently in the engine room, revealed itself as a force that could tear through walls, lives, and livelihoods in a heartbeat. The scale of destruction was unprecedented. Debris was scattered across the mill complex, and fragments had reached areas that engineers had once assumed were safe. The sheer distance traveled by shards of iron stunned observers. Some pieces had flown hundreds of feet, crossing rivers and streets, embedding themselves in buildings where workers and families had gathered, completely unprepared. Entire operations ground to a halt, looms, presses, pumps, all powered by that single spinning giant, stopped in unison, leaving workers stranded amidst the wreckage. Factory owners faced the staggering cost of repairs. Engine houses were often rebuilt at 5 times the value of the flywheel itself, yet the flawed design persisted. Why? Because despite repeated disasters, the core industrial logic hadn't shifted. Flywheels were efficient, they were proven, and their danger, though apparent in hindsight, was normalized in practice. The disaster highlighted a shocking truth: efficiency had a human price. But the impact extended far beyond the factory walls. Streets filled with panicked workers and onlookers. Families, hearing the explosion from miles away, rushed to the mill gates. Rumors spread faster than facts, creating fear and confusion across the town. Emergency protocols, if they existed at all, were non-existent for this type of disaster. Unlike fires or boiler explosions, high-speed iron had no visible warning, no whistle, no steam, no alarm. Communities realized that the very machines meant to fuel industrial growth could also transform entire towns into zones of unpredictable danger. Investigators arrived to measure the carnage. They documented broken masonry, shattered timbers, and fragments weighing hundreds of pounds lying across yards. Casualties were tallied, but numbers alone failed to capture the chaos. Workers had been injured in multiple buildings, some outside the factory grounds, illustrating a terrifying reality. Energy released indoors can ripple outward uncontrollably, turning a single mechanical failure into a citywide incident. Insurance underwriters began to take notice, but regulation was slow and fragmented. Industrial accidents like this highlighted the gaps between engineering theory, human labor, and the urban landscape. The emotional impact was just as severe. Workers now understood that their day-to-day environment, machines humming, wheels spinning, engines roaring, was a constant potential death trap. Fear and respect became intertwined. Survival required vigilance, trust in experience, and luck. For townsfolk, it shattered confidence in industrial expansion. The line between productivity and peril had blurred. Ultimately, the disaster left a lasting lesson. Massive energy concentrated in a single object is not just a technical challenge, it's a social one. The Amos-Gay disaster forced industrialists to ask uncomfortable questions. How do we protect human life without sacrificing productivity? How can we respect energy's hidden power? And crucially, how do we rethink an entire system that puts entire communities at risk? Next, we will move into Chapter 8, Moral Legacy,
exploring how these disasters reshaped industrial engineering, safety culture, and the design philosophy of modern machinery.
The story of the hidden giants, the massive industrial flywheels, doesn't end with shattered bricks or the haunting images of flying iron. Their true legacy lies in the lessons they left for engineering, industry, and human life. These disasters forced a reckoning. If a single spinning wheel could destroy factories, injure workers, and disrupt entire towns, then efficiency alone could no longer justify risk. The question became clear. How do we balance raw industrial power with safety, foresight, and responsibility? After decades of accidents, engineers began rethinking the invisible forces they had once considered controllable. Flywheels taught them a hard truth. Energy cannot simply be stored and ignored. It must be contained, managed, and respected. Factories began implementing structural changes. Engine houses were reinforced, flywheels enclosed or relocated, and emergency protocols developed. Material science advanced. Steel replaced cast iron because, unlike brittle iron, steel could bend under stress rather than shatter catastrophically. Speed limits were imposed, governors improved, and maintenance routines intensified. These changes weren't just technical, they reflected a shift in the ethical responsibility of engineers toward human life. Perhaps most importantly, the legacy of flywheel disasters reshaped the very philosophy of industrial design. Safety became a design criterion, not an afterthought. Engineers learned to anticipate failure, to build systems that didn't just perform well, but failed safely when failure was inevitable. Containment, redundancy, and modular design, all concepts familiar to modern machinery, were born from studying the devastating consequences of concentrated energy. In many ways, the flywheels were the harsh teacher, and history became the textbook. The societal impact was equally profound. Insurance companies, once passive observers, began requiring safety measures, effectively forcing industry-wide adoption of better practices. Workers, now aware of the invisible dangers around them, gained leverage to demand safer working conditions. The repeated disasters turned public attention toward industrial accountability, showing that human lives and communities could no longer be collateral for efficiency. Every spinning giant that failed became a story, a warning, and a catalyst for change. Even as electric motors replaced massive flywheels, reducing energy concentration and localized risk, the lessons endured. Modern machinery, from power plants to factories, carries the imprint of this past. We build with containment, anticipate failure, and respect stored energy. The Amiskane disaster and countless others remind us that innovation without caution can be deadly, and that every machine, no matter how silent or smooth it seems, has the potential to unleash forces beyond our perception. Finally, the moral legacy of these hidden giants extends beyond engineering. It's a human lesson. Curiosity, ambition, and ingenuity must be tempered with foresight, empathy, and respect for the unseen power around us. The flywheels were more than metal in motion. They were a mirror, reflecting the stakes of industrial progress. Their story challenges us to look at all systems we depend on, mechanical, societal, even digital, and ask, are we controlling the power, or is it controlling us? In the end, the hidden giants left a gift. Not just a record of destruction, but a blueprint for safer, smarter, and more responsible innovation. And that is a legacy that spins on, invisible but vital in every modern factory and every engineered system that carries power safely into the future.